All right, so now we're going to go back and talk about something that we talked about last week, and it's actually a couple of chapters ago. It's constitutional isomers. You've seen this before, so I'm going to keep this video short. So isomers are different structures with the same molecular formula. Different structures with the same molecular formula. We're going to see a couple different kinds of isomers this term, but constitutional isomers you've already seen. We're just going to come back and touch on it again. So constitutional isomers means that the atoms are connected differently. They're also called constitutional isomers. Did I just say that? I'm not sure what I said, okay? They are called constitutional isomers. I might have just said constitutional isomers are also called constitutional isomers. All right, so let's think about this for a second. In one of your first homework assignments, you were asked draw all the constitutional isomers for a particular formula. And so we think back to this. Remember this? Can you see this from where you're sitting? C3H8. There's only one way that you can connect all the atoms C3H8. There's only one way. And so C4. So that would not be a good question for such a question, right? You wouldn't say draw all the constitutional isomers for C3H8 because there's only one way you can do it. I encourage you to stop the video right now and prove it to yourself. Pull your pencil and paper out and try to make carbon, carbon, carbon with 4 bonds each and hydrogens all with 1 bond. See if you can do anything except that one constitutional isomer, okay? So, or that one structure. So look at C4H10. Now, there are more than one way you can do C4H10. If I can use line bond structures, these are the 2 constitutional isomers for C4H10. C5H12 is 1, 2, 3, 4, 5. 1, 2, 3, 4, boom, or 1, 2, 3, 4. Those are the 3 isomers for C5H12. C6H14, I'm not going to take the time for that because you can see it goes up to 5 constitutional isomers, right? C7H16 would be a long effort. C8H18 would be even more so, and you can see pretty fast it goes up a big deal. Now, this isn't really fair because we never did like C11H24, but you can see it goes up pretty fast. All right, so as the number of carbon atoms increases, the number of constitutional isomers increase, of course, because there's more ways to connect things. All right, be able to recognize different structures as being isomers or being the same compound. There's 2 ways to do this. One way, of course, is just to flip it around and see if you have the same thing. For example, if you've got that structure and you've got that structure and you know that you have free rotation about that bond, can you see that? Then you know these are the same thing, right? So you can just flip it around in 3D space and rotate it and see if you can make 2 structures be exactly the same thing. The other way to do it, in my preference, is to name them. If you name them very carefully and they have the same IUPAC name, they're the same compound. All right, and then finally, 180-degree rotation around the C3-C4 bond would make it more obvious, for example, that these 2 compounds are the same. Can you see this is the C3-C4 bond right there? Can you see that? And if you flip that around, it would end up being 180 degrees would bring it up here, right? Flip it around and bring it up there, and then I think it'll be more easy to see that you have these are the same thing. But I still think that's not the best way to do it because that requires some, I don't know, flipping things around, and then you might think you can't do it when in fact you can. Really, the rock solid way is to name it with IUPAC rules and see if they get the same name. If you do, you have the same thing. If you don't, you have constitutional isomers. That is, of course, if they have the same molecular formula. All right, good luck.